Okay, we're recording now. Fantastic. I'm not gonna go through everything that I just said for the interest of time. But point is that if you did go ahead and send me, your stuff, I will get everything back to you no later than Wednesday. Does classwork count as participation? No, classwork will not count as participation because classwork is something that I can't see that you're doing. The reason classwork is assigned is because classwork is just supposed to be a couple extra questions for you to try to do while you're doing the material. It's almost like homework for, even though, it's because of the fact that this is an online class. But I still wanted to include questions as part of the lecture for you to try on your own. And that way you can try it on your own and also we go through it together. So classwork is separate from participation. The things that impact your participation are your, showing up. Again, I don't necessarily grade you particularly on attendance, but showing up, answering questions, and asking questions. If you're doing those three things, then your participation score is going to be fine. If you're not answering questions specifically, especially when I'm calling on you, then you can kind of expect your participation score to be lower. So. But in any event, I see that Deborah is asking for 79, so we can go ahead and get started with that. So we will just go ahead and attack this homework. If anybody else has any other questions, feel free to throw them into the chat, and we will address them. Okay? So, 79. All right. Let's see which one that is. So 79, we had to evaluate the logarithms, right? So we had log of a log. So that's always fun to deal with. In fact, I believe on your project packet, there is an example of that as well. There's log of a log of a log on your project packet. Now, for the record, I will say that the hint that I gave you for attacking the homework and the hint for, I haven't started sharing my screen. Sorry, Aline. But anyway, yeah. So the hint that I gave you for the homework and the hint that I gave on your project packet are exactly opposite. And the reason that they're opposite is just because one helps you more than the other. So for the homework, I said try evaluating the inside logarithms, one at a time. So you do the inside logarithm first, and once you've evaluated the inside logarithm, then you do the outside logarithm, right? So I'm going to start sharing my screen now, and I'll tell you guys exactly what I mean by that. But with the project packet, it helps. It makes the question a lot easier to attack it from the outside first. But in any event, we'll deal with the homework first. And if you guys have questions about the project packet, of course, feel free to see me during office hours. Okay, so 79 is we have log of base 4 on the outside. And then on the inside, we have log of base 3 and it's on the value 81. Okay, and again, the hint that I said is go ahead and do the inside logarithm first. So if you guys had questions on 79, hopefully you at least were able to get through 35 and 37. If you could do 35 and 37, you could probably do 79 and 80 if you sat there long enough beating your head against the wall. So the idea is first we're gonna take the value of this guy here. We're gonna figure out what log base 3 on 81 gives us. Okay, so what we're gonna do, and I'm just gonna underline this in red, and then we're gonna do this in red here. So first we're gonna do log base 3 of 81. And whenever you're evaluating a log, whenever you're given a logarithm and it says evaluate, the very first step that I detailed in the lecture is you want to set it equal to a variable. So you set it equal to x. Okay, so we just set it equal to x. And the reason that we do this is because it's obviously an unknown number. We don't know what that number is, so we could assign it a variable. And now that we have an equation, and now that we know that it's equal to some variable, we can translate this from logarithmic form to exponential form, and that's going to help us solve this. It'll make things a lot easier. So how do I translate this to exponential form? Let's see. Okay, so Sophia, if you could help me out, how do I get this to exponential form? First off, why don't we start with what is my base? So if we're talking about this logarithm right here, this logarithm has a base. So it's either going to be 3 or 81. So if you don't know, you have a 50-50 shot. Okay, so if not Sophia, then let's say Keji, can you help me out? What's the base of this? 81. Okay, so 81 is the value. This is the base of a logarithm is always going to be the lower piece here. Think about when you see the word base, or when you hear the word base, 3. Yeah, I mean, you had a 50-50 chance, right? If you say both, then you'll obviously get the answer. So cool. When you hear the word base, obviously, think about like foundation, right? If you see like the base of a tree, you think like the bottom of a tree, or possibly the roots, right? The trunk. If you hear like the base of a building, you're talking about like, the bottom portion of it, the foundation of the building, right? So the base of a logarithm, you just think, oh yeah, what's the bottom number here? And the lower number is 3. So the base of the logarithm is 3. And then we have this value 81, and then our x on the right-hand side, right? So when we translate a logarithm to exponential form, we know that we're going to have it in the following form, right? Exponential is where we have a to the x is equal to y, right? Where a is your base, x is the exponent, and y is the value, right? So what is the exponent in a logarithm? The exponent in a logarithm is what you're solving for. It's when you evaluate it, what you get on the other side. X is essentially the exponent. When you do again, a logarithm is set up to where the exponent is essentially the answer from the equation. So we don't know what the exponent is, but we know that, okay, well, clearly it's going to be our exponent here. And again, we know what our base is. Our base is 3. So the left-hand side is going to be 3 to the x. Okay, sure. And this is equal to whatever my value was that was attached to the logarithm. So in this case, 81 has to be our y. So we have 3 to the x is equal to 81. Okay, so again, the idea is in a logarithm, your base is going to be the lower number, your value is going to be the number that's attached to the y, and the exponent that you're solving for is what's on the other side. And in exponential form, it's just flip that, right? You still have your base, but it's your base being raised to an exponent, which gives you that value. So that's how logarithms and exponential forms, go hand in hand. Okay, so now we have the following equation. We have 3 to the x is equal to 81. And what I said in the lecture is as long as your base isn't 0 or 1, which it shouldn't be because a logarithm and an exponential form are both not valued, or they're not exponential functions if your base is 0 or 1. So as long as your base isn't 0 or 1, what you can do is if you can get the left-hand base to be the same thing as the right-hand base, then you can just set the exponents equal to each other and make a new equation and solve for your variable. So we have to play a game here. Our game is we need to make this base and this base look the same. Currently, we have a 3 and we have an 81, right? So we have to manipulate these so that way they look the same. So the first thing that should run through your mind is, okay, well, I have a 3 over here and I have an 81 on the right-hand side. Now, you start thinking about how you can break down 81, how you can manipulate it with exponent rules. So you say to yourself, okay, well, I know that 81 is 9 squared, right? I know that 81 is the same thing as 9 times 9. So start there. Just start simple. If you don't see it immediately, that's okay. Just break it down one step at a time. So 81, it's the same thing as 9 times 9, so that's fine. So 9 times 9 is 9 squared. Cool. So, okay, what you just did is it was originally 81 to the first power. You used an exponent rule that you had, and you broke it down to be a different base raised to a different exponent, right? 81 to the first power and 9 to the second power are still equivalent. We just changed the form of it. And we say to ourselves, okay, we're getting closer. 9 is a lot closer to 3 than 81 is, but obviously 3 and 9 are still not the same base. So we need to keep changing 9 until it looks like 3. But we know what 9 is. 9 is just 3 squared as well, right? So this is 3 to the x is equal to 3 squared, and we still had that original square outside from the first thing that we did, right? And last but not least, and I'm not going to go through this one too much because this is one of the exponent rules that we keep seeing over and over and over again. But when you have a base raised to an exponent raised to a second exponent, you just multiply the exponents, right? So we have a base raised to an exponent raised to a second exponent. So you would just multiply the exponents together. 3 squared to the second power is 3 to the 2 times 2, and 2 times 2 is just 4, right? So you have 3 to the 4th power. And great, now we have a 3 here, we have a base of 3 here, so what we can do is we can just set our exponents equal to each other. And in this case, our work is done. We actually don't have anything else to solve for. We just say, great, x is equal to 4, and yeah, that's it, we're done. X is equal to 4. So when we go back to this original logarithm up here, so log base 3 on 81 is equal to 4. So what we just did is we solved the inside logarithm. We found a value for the inner logarithm. Log base 3 on 81 gives you a value of 4. So what we can do is now we can set an equal sign, right? And we can kind of simplify this logarithm. It's now no longer 2 different logarithms. It's now just one, right? It's log base 4 on the value 4. We figured out what that first one was. And now we just do the same thing again, right? Now we figure out what this piece is. What is this logarithm? Well, we have a logarithmic rule for this. This was in the most recent lecture where we went over 4 logarithmic rules. But if you don't remember them, that's okay. You can still figure it out without the rules. The rules are there just to make your life easier. If you can memorize the rules, your life is substantially easier. But if you can't memorize them, then that's totally fine. Again, you just translate this into exponential form, right? So we have, and again, I'm just going to underline this in green. We're going to do this work one more time. So log base 4 on 4. I want to translate this to exponential form. Let's see. Taylor, help me translate this to exponential form. So first thing, very first thing, if I'm trying to evaluate a logarithm, what do? I have this logarithm right here. What do I do with this? What was the very first step that we did right over here? We had this piece here. What did I do the first thing?
I'm not sure. I'm just a little confused. Sorry.
Okay. So first thing that you're doing, again, when you're evaluating a logarithm, is you set it equal to a variable. You set it equal to x. Okay? Yes. Zenaida, did you have a question, or were you just answering the question?
Yeah, I just want the answer.
Oh, okay. Sorry. Okay. So, well, why don't you pick up from here, Zenaida? So if I want to translate this to exponential form now, right? I set it equal to a variable, right? So I have log base 4 on 4 equal to x. So I want to get it into an exponential form. An exponential form, again, is when it's a to the x is equal to y, right? So first off, what's my base, Zenaida?
A 4.
4, right? My base is this piece down here, right? So that's 4. So I know that I'm going to have a base of 4 here. What's my exponent?
X.
X, right? Perfect. My exponent is the variable that I just assigned. So great. And then lastly, what is the value that's on the other side?
4 again.
It's also 4, but it's this one, right? So
yeah.
Perfect. So it's 4 to the x is equal to 4. And now you just ask yourself, okay, what is my hiding power of the 4 that's on the right-hand side? Well, it's 1. Right? And now we realize we have the same base on the left side as we do on the right side. So what we can do is we can just take our exponents and set them equal to each other. So we can just take our x and our 1 and set them equal to each other. So x is equal to 1, and we're done. And so when we come back up here, when we were evaluating, we first simplified the inner piece, right? The underlined in red piece, and we got 4 from that. Then we had log base 4 on 4, and when we just evaluated that, well, it's just equal to 1. So that's our final answer. So I know Taylor said, that they were confused. Does anybody else, does anybody have questions on this? The idea, again, the hint that I gave you is evaluate one log at a time, starting with the inner one and work your way out. If you understood how to evaluate logarithms, then you should be okay. But obviously, this is a bit tricky. This is not something that, you know, if you've never seen this before, I'm sure this looks incredibly ludicrous, trying to go from a logarithm to an exponential. It's definitely not intuitive. So please ask me questions now. I'd very much like to answer them if you have them. Yes, Deborah.
I don't know what just happened because my internet just crashed.
Okay, so I'm not going to go through the entire problem again, but you know, obviously
Just the ending.
Just the ending. Okay, so the idea is, once again, we had a second logarithm, right? We found the value of 4 because of what we did earlier. So we had that 4 in there. We set it equal to a variable just like we did the first time. We translate it to exponential form, which is, you know, a to the x is equal to y. That's an exponential. When we translate it, we get 4 to the x is equal to 4, and 4 on the right-hand side is 4 to the first power. So we know that the only exponent that makes this equation true right here has to be x is equal to 1, right? If you have the same base 4 here and you have the same base 4 here, and this is 4 to the first power, the only way that this equation could possibly be true is if this exponent matches this exponent, right? So that's why you're setting your exponents equal to each other. But there's no work to be done here. This is not 4 to the 2x. If this were, you know, 4 to the 2x, then of course you'd have to solve for x. But solving for x here, x is equal to 1, you're done. You don't, you know, there's no work to be done for solving for x. So we get x is equal to 1, and that is the final solution for the entire logarithm on the logarithm. Okay? Any questions on this? Again, the idea is just that you're going freely back and forth between a logarithm form and the exponential form. So you should really, you know how to do that. And if you don't know how to do that, now's the time to ask. Okay, we're gonna keep going then. So 80 and 80. Okay, yeah. So number 80 from Olivia. Sure, we can hit that one up as well. So number 80 here. This one is the same idea, right? So instead of 2 logs, now we have 3 logs, right? So we have 3 different logarithms that we have to kind of evaluate one at a time. So we have log with a base of 4, log with a base of 3, and log with a base of 2 on the value 8, right? So it's that piece and that piece. Okay, so what's really going on here? First off, we have the innermost logarithm, right? Which has some value, which in this case is 8. And so that means that we can definitely evaluate the inner piece. Once we evaluate the inner piece, we're going to get some number back, right? We're going to get some value from setting this up into an equation, translating this into exponential form, and solving. So once we get a value back, we will then have a value for the logarithm which has a base of 3. So then we can play that same game where we do it all over again, but this time with, you know, the value that we got from doing the red piece. And then once we get a value back for doing the piece in green, we can then do the entire final logarithm, which has the base of 4. Okay, so you're handling one logarithm at a time with the information that they gave you. So the one that's most easily able to be done is the innermost piece, because you have the most information to be able to solve it. You have log with a base of 2, and you have a value attached to it. So let's handle the red piece. We're going to do log base 2 of 8, and then we'll, you know, go from there. Okay, so we have log base 2 of 8. Okay, once again, when you're evaluating a logarithm, you always set it equal to an exponent. Okay, so we set it equal to x. Great. And when I say an exponent, sorry, I meant a variable. You set it equal to a variable, in this case, x, because the other side of your equation, you're essentially always solving for your variable, right? Or for your exponent that is from your exponential function, right? This here, these x's go hand in hand. The exponent that is attached to your base in the exponential function is your answer from doing the logarithmic equation. Okay, so we set this up, and again, we're trying to get this to where it's in the exponential form. So we ask ourselves, great, what is my base? My base, once again, is the lower number of the logarithm, right? It's going to be this 2. So my base, which is a, is 2. Then we ask ourselves, okay, what is my exponent? Well, exponent is the answer from the logarithm, and we don't know what it is yet, right? So when we translate it to exponential form, it's still just going to be our variable. So it's still 2 to the x. And last but not least, the variable on the right-hand side, that y value, well, that's going to be the value that is attached to the logarithm. So that is going to be my 8. So we get 2 to the x is equal to 8. Okay? Once again, you are always just playing the same game once you get it into this form. You're trying to translate one of the bases to look like the other, or maybe you can even manipulate both of the bases. But either way, you're trying to get the bases to match, right? So right now we have a base of 2, and we have a base of 8. If I can get them to match, then we can just set the exponents equal to each other. So I have 2 to the x here, and I'm going to manipulate the right-hand side, but of course, understand you can absolutely manipulate the left-hand side just as easily, and I can run you guys through that really quickly. So yeah, Shelby's absolutely right. It's 2 cubed, and the way that we get 2 cubed is you realize, oh yeah, 8 is just, a power of 2, right? If we multiply 2 times 2, we get 4, and multiply by 2 again, we get 8. So that's really just 2 times 2 times 2, which is 2 cubed. So 8 is the same thing as 2 cubed. So we get 2 to the x is equal to 2 cubed. And now we have the same base, right? We have 2 on the left, we have 2 on the right. And as a result, we can now set our exponents equal to each other, right? So we now set x is equal to 3. And yeah, great, we're done. X is equal to 3. So that means the inside most logarithm, this piece right here, when you evaluate it, is just 3. So when I simplify this, and I'm going to put an equal sign here, and we're just going to simplify this one at a time. So we have log base 4 on log of base 3. And now, again, what we're plugging in here for log of base 3 is we're plugging in a 3 now. And the reason we're plugging in a 3 is because that is what we got from handling the first logarithm. Okay? So now we do the same game all over again. We just do this inside logarithm. But we have a rule for this one. So last time we handled the logarithms, and I said there was a rule, and if you don't remember the rule, that's okay. You can, absolutely tackle it. But let's try to just do this one using one of the rules that we have. So in green, log base 3 on 3, without setting this equal to a variable and converting it to exponential form, we have a rule that says if we have the same base, and I'll write it over here, if we have the same base as we do the value that's attached to the logarithm, if these two pieces match, the value that we should get back is always 1. Every time. You should always get a 1 back. So, okay, we ask ourselves, do our numbers match? We have a base of 3 and a value of 3. So yeah, we should absolutely just be getting a 1 back. So we know that the inside logarithm is just 1. And if you don't see how I'm getting that, if you don't remember the rules that, I went over in the lecture, that's okay. Once again, you can absolutely solve this doing your normal method, right? So you set it equal to a variable, in this case, x, and then you say, okay, converting it to exponential, I take my base, which is 3, I take my variable, which is my exponent, and I set it equal to the value that's attached to the logarithm, so the other 3. This has a power of 1. And so when you compare the exponents, because they have the same base, yeah, of course, x is equal to 1. So we get the same thing either way. So x is equal to 1, which tells us now the inside logarithm just basically goes to 1. So we have log base 4 of 1. And now we just need to finish this guy up here. And once we're done with this logarithm, we'll then be done with the entire answer. Right, so I'm just going to do this one in blue now. We're handling this piece. And so we have log base 4 on 1. We set this equal to a variable one more time, right? So the idea is we're converting it to exponential again. So convert it to exponential. Who can help me out? One more time. Ashley, if you can help me out, that'd be great.
It would be 4x equals 1.
4 to the x is equal to 1. Perfect. 4 to the x is equal to 1. Great. Okay. So we have 4 to the x is equal to 1. what are we going to do here? What are we going to do? Okay, well, 4 to the x is equal to 1. Let's see. The idea here should just be that we're going to try to convert 4 to the x equal to 1 and see what we get. Is there anything that we can do with this? Well, we know that, again, log base 3 of 3 gave us 1, so that's where we got this piece from. And then 4 to the x is equal to 1. Well, is there any number that is going to make the 1? So this is the only one here where you can't just set your exponent to equal the other exponent on this side. You actually have to think to yourself, what value is going to give me a 1? What value for my variable? But you always know any number to the 0 power gives you a 1, right? So when you say 4 to the x is equal to 1, there's only one possible number that makes this true. X has to be equal to 0. This one you were only able to do, like this logarithm here in blue, you're only able to do by inductive reasoning. There's no like mathematical way that you can actually show this. This is purely just off of one of our exponent rules. If you have 4 to the x is equal to 1, then you just have to understand that when you plug 4, when you have any base raised to a 0 power, you're always going to get 1 back. So just by default, x has to be 0. If you had any other exponent, any, 1, 2, 3, so on and so forth, the left and the right-hand side would never equal each other. Keji, yes?
Sorry, I didn't mean to do that.
Okay, sure. So again, the idea here is just that 4 to the 0 power, if we're just writing this out, 4 to the 0 power, is equal to 1. And so you know that 1 would equal 1, and hooray, you're done. Okay, so we get x is equal to 0, which means that when we finally finish this up, yeah, you're done. And there is a rule that we had for this. And of course, the whole idea here is that if you forgot the rule, you just had to use inductive reasoning here and just be like, okay, yeah, of course, x had to just be 0 because how else would this equation work? But we do have a rule that says if you have any base, so, and I'll write it above here, so log of any base, and your value is 1, the right-hand side is always going to be 0. That is one of the 4 rules that we talked about in the lecture. Okay, so hopefully that's not too bad. Again, the idea is, notice that we had 3 logarithms, and we had 3 times that we converted the logarithms, right? So the answer is just 0? Yes, the answer is just 0. Amanda left class because her Wi-Fi went out, and yeah, that's totally fine. It happens. So again, notice we have 3 logarithms, so we have 3 times that we converted from logarithmic form to exponential form. We couldn't do the outside ones first because we didn't necessarily have the tools available to do the outside ones first. You could try it and it might work out, but it's just far easier to try to handle the inside pieces and work your way outward, right? So log base 2 of 8, you can figure that out. You figure out that it's 3. So you evaluated log base 2 of 8 to just be 3. So this entire piece in here would just evaluate to be 3. And then you figure, okay, well, log base 3 of 3, well, when you do this piece would just be, okay, log base 3 of 3 gives you 1. And then log base 4 of 1, well, then this entire piece would just be 0. And that's it. Okay, so you're evaluating one chunk of information at a time by converting the logarithms to exponential form. And that's all there is to it. So if you understand how to convert to exponential form and how to solve for your exponent, then you're totally golden. But if you don't have questions, or I'm sorry, if you don't understand that, then obviously this makes no sense to you, and so you should ask questions. But in any event, yes, the final answer here is just 0. Okay. Any questions on this or any other questions that you guys want to go over? I think Keji said 57, so we can definitely hit on 57 here. Actually, I wanted to make time for 57 if nobody was asking any other questions. So that's perfect. So we're gonna touch on 57 here, and then we'll try to make room for whatever else that we can with the remainder of class time. So 57. The idea here is we're trying to find domain. Again, this never goes away, right? Domain is the bane of algebra students. I know it is. So domain, we have f of x is equal to log of x minus 2 plus log of 2x minus 1. Okay, so domain of a logarithm. Now, there's something that we talked about a little bit in class, but I really didn't hammer this down. So you had to really be paying attention to really be able to do 57. For the domain of a logarithm, the value that's inside the logarithm has to be positive. That has to be a positive number. So for both of these pieces right here that's underlined in black, these both have to be positive. They can't be 0 and they can't be negative. Okay? So the domain of, and the reason for this, I didn't necessarily say it explicitly like that, but I did say that if you have a logarithm in this form, that x had to be greater than 0. Okay? So what are we going to do here? Again, we understand now that what we're looking for is we're looking for positive numbers only. So what you have to do is you have to take each logarithm and set it to be greater than 0. And when I say each logarithm, I mean just the value that's attached to the logarithm. Okay, so in this case, x minus 2, we're going to set this to be greater than 0. And on the other hand, 2x minus 1, we're going to set this to be greater than 0. Okay, we're going to find the domain of each piece, so of each logarithm, and then because both logarithms are part of the same function, we have to see where the domains of both of these agree. So we're going to check the domain of the left one, and then we're going to check the domain of the right-hand one, and then once we find the domains of both, we're going to see where they agree, and anywhere that they don't agree, we exclude that from our domain, because again, it's all part of one singular function. So if it doesn't work for one of them, but it works for another one, that's still not okay, because it has to work for both. Okay, so, all right, left-hand side one isn't too bad. We have x minus 2 is greater than 0, right? Again, we set it to be greater than 0 because it has to be a positive number. So, okay, that means when we solve for x, we have x is greater than 2. And should this work out? Well, yeah, this is saying that if we plug in any number for x that's bigger than 2, we're going to get a positive number, right? Because if you plug in 3, for example, you get 3 minus 2, which is 1, which is a positive number. Hooray. Yeah, that's exactly what we want, right? So the domain of this piece, if we write it in interval form, is we're talking about all the numbers starting from 2 that get larger from 2. And we're not including 2 because if we include 2, then we're including when the value of our logarithm is 0, and that's not part of our domain. So we have to say, okay, it's 2 with a parentheses because we're not including it to infinity. Okay, easy enough. Let's go ahead and do the right-hand side one. So if I can have Deborah, since I don't think I've called on you in a little bit, if you can help me out, solve for x here. For this piece.
It will be 2x equals.
So 2x is greater than 1. Yep.
Yeah, greater than 1. And
okay.
X is greater than a half.
Yeah, by dividing both sides by 2, x is greater than a half. Perfect. Okay. And then, Deborah, if you could write this in interval notation for me, what is this going to look like? So, this piece right here, essentially.
For x is greater than a half.
Yep.
X equals parentheses.
Okay, so we have the parentheses.
Half comma infinity.
Half comma infinity. Perfect, right? So again, the idea is we're talking about all the numbers starting from a half that get larger and larger and larger, right? They go on forever, and any number that's bigger than a half is going to satisfy the right-hand side, right? So if you don't immediately see the points that you have to exclude, if you don't see the problem immediately, that's okay. Put it on a number line. Throw your domains on a number line and see where they don't match up, right? So for the purpose of this, I'm just going to put this guy over here in blue, and this one over here is going to be in red when I plot this on a number line to really make this stand out, right? So here's my number line of my domain. These are all the possible inputs that we can plug in, right? And we know that we're going to have a half, and we know we're going to have a 2 over here. Okay, so for 2 to infinity, which again I'm going to notate in blue, 2 to infinity is starting from 2, not including 2, and it's all the numbers that get bigger than 2, right? So all of those ones over there, and actually I'll put it above just to make it cleaner, as such, right? And now from 1/2 to infinity, well, that's starting from a half, still not including a half, and it's all the numbers from 1/2 that also go to infinity. Now notice, we have a part that looks, that matches up, right? If we're talking about this section right here, this section works. But we have to ask yourself, okay, well, what is the section that doesn't work at all, right? What are the pieces where they contradict, where they don't agree? And that piece is going to be right here, right? That all the numbers from 1/2 to 2, you can't include. Because if you try to include, say, for example, 1, well, 1 is going to work for the right-hand logarithm. If you plug 1 into the right-hand logarithm, you get 2 times 1, which is 2, and 2 minus 1 gives you 1. So yeah, you get a positive number for the right-hand one. But in the left-hand one, if you plug 1 in, you get 1 minus 2, and that's clearly not a positive number, right? So we have a problem. So we can't include the numbers between 1/2 and 2. Those are not going to be acceptable. So our final interval, our final domain here is just going to be the numbers from 2 to infinity, because those are the points where both of the domains agree. Okay, so that's your final domain. So again, just to kind of go over this one more time, we started with our function. Our function had 2 logarithms, so we had to find the domain of both logarithms. To find the domain of a logarithm, that means that your inside value has to be positive, so you set whatever your inside value is to be greater than 0. Once you've set it greater than 0, you essentially solve for your variable, and you're going to get an interval. When you get your interval, great. You get an interval for one, you get an interval for the other, and you just cross out the points that don't make sense. The points where, they might work for only one of them, but they don't work for both of them. The only points that are going to be in your final domain are the values that you can plug in for both of the logarithms without one of them failing. So in this case, from 2 to infinity, all of those numbers will work, but the points between 1/2 and 2 only work for one of them. So this is our final answer. Any questions on the process that I took here? Any questions at all, rather? Domain isn't really a new idea, but of course, if you weren't really paying specific attention, this was probably really hard for you to figure out that you had to do this step right here, right? Setting it to be greater than 0. If that part is what was holding you up, then fair enough. But after seeing it, if you still have questions, let me know. Zenaida, yes.
If those values in there are positive, should we still set it to greater than 0, right?
So I'm sorry, are you saying if you just have a regular number in there?
Nah, say it was x plus 2, it will still be set it to greater than 0.
Yep, exactly, right. So if I'm just going to put it hypothetically over here, let's say we had log of x plus 2, that's what you're saying?
Yeah.
Okay, so yeah, so you're still going to take your inside value, because notice that you're going to include more numbers in your domain, but it's still not going to be all the possible numbers. So you set x plus 2 to be greater than 0. You solve for x by subtracting 2 on both sides. You get x is greater than -2. So now notice that you still have a stopping point here, right? We're talking about all the numbers from -2 to infinity. If you tried plugging in -3, for example, it's not going to work, right? -3 plus 2 still gives you a -1. You still get a negative number. So yeah, even if you have addition going on, that you're still setting it to be greater than 0. Okay, good question. Any other questions that you guys may have? Okay. So for the interest of time, I'm just gonna, Deborah, I just answered one of your questions before. I'm just gonna go to Gianna's 37, and if we have time, I'll double back to 86. Okay. So 37 hopefully won't take us too long, but we'll take a look at it nonetheless. So 37, we have log of base 3 on the square root of 27. Okay. I included this question for a very particular reason, because we had a lecture talking entirely about rational exponents and how rational exponents relate to roots or radicals. So we have the square root going on. And in your process here, 37 is asking us to evaluate this logarithm. So your process is still the same. You're still going to set this equal to, a variable. So we said, okay, log base 3 on 27 gives us some number. So when I convert this to exponential, if I were just to convert it to exponential immediately, well, we have 3 to the x is equal to square root of 27. But what the heck is square root of 27? How are we going to possibly convert this? This looks awful right now, right? So the step that you had to realize is that square root of 27 is the same thing. If you have, square root of any number, it's the same thing as that number to the 1/2 power. Okay, remember that radicals or roots, whatever you want to call them, these are essentially exponents, fractions, right? The index tells you the denominator, and the power on your, the number that's underneath the radical tells you what the numerator is of your fraction. So for square root of 27, we can convert this and we can say, okay, well, this is really, so 3 to the x, this is 27 to the 1/2 power. Once you got this far, hopefully the rest wasn't super bad, because you could say to yourself, okay, well, 27, I know that that has 3 as a factor, so you can go through and figure out how many times you would possibly try to multiply 3 against itself to give you 27. You would change the base just like we did before, and when the bases match, you just compare the exponents, right? So we have 27, and again, you can say, okay, well, what really is 27? 27 is just 9 times 3, right? So 27 is 9 times 3. And again, we're trying to keep in the back of our heads we want it to be in the form of 3, right? But what is 9? Well, 9 is 3 times 3 times 3, which is just 3 cubed. So, okay, well, now that we know what 27 is, we can change that to be a power of 3. So we have 3 to the x is equal to 3 cubed to the 1/2 power, right? And what can we do when we have a base raised to an exponent raised to a second exponent? We can just multiply them together. So we have 3 to the x is equal to 3 to the 3/2, right? When you multiply an integer by a fraction, you to the numerator. So 3 times 1 up top gives you 3, and it's still over 2. So you get 3 over 2, and that means that your final answer is 3/2. So this logarithm over here just gives you 3/2 as an answer. Okay. Again, the step that was absolutely the hardest was remembering how to convert square roots or any radical to a fraction exponent or a rational exponent. Okay. So as long as you remember your index is your denominator and the power on your radicand is going to be your numerator, then you're in good shape here. And you can convert it to be 27 to the 1/2. And from there, you're just changing the base of 27 to be in terms of 3. Of course, you could also do something similar. You could also change for all of the examples that I've done so far, I've been converting the right-hand side. So I've been converting, in this case, 27 to be look like the base of 3. You can absolutely also convert 3 to look like 27. So how would I go about doing that if I wanted to? So you ask yourself, okay, well, what really is, if I wanted to convert 3 to be, to look like 27, 27 to the 1/3 power is equal to 3, right? If you don't see where I'm getting that from, remember, we just talked about 27 is the same thing as 3 cubed, right? So if I wanted to convert my 3 to have the base of 27, all I would do is, take the cube root of both sides. Taking the cube root of both sides, I have my base of 3 here now, right? And this is the cube root of 27. Cube root of 27, you can always just convert that to be 27 to the 1/3. Remember, your index of your radical sign is going to be the denominator of your rational exponent. So that's going to be the 3 right here. And then it's 27 to the first power underneath of it. So we know that it's, a 1 up top, right? So what I could have also done is I could have said, okay, well, instead of it being 3 to the x on the left-hand side, and I'll write this in blue over here just so we know this is an alternative. So the alternative that you had is you could have said, okay, well, 3 to the x is equal to square root of 27. I'm going to convert 3 to look like 27. So this is 27 to the x over 3, right? It was originally to the 1/3, but we multiplied that other power of x to it. So 27 to the x over 3. And this is equal to, again, 27 to the 1/2. And now that we have the same base, you just compare the exponents, right? So we have x over 3 is equal to 1/2. And all you're going to do to solve for x is multiply both sides by 3. X is equal to 3/2. Either way, you get the same answer. One is maybe a little bit more intuitive than the other. So the right-hand side, probably a little bit more intuitive, just trying to convert 27 to look like 3 rather than trying to convert 3 to look like 27. But it's absolutely doable. Either way, however you want to go about it, it's 100% accurate and totally mathematically okay to do it either way. Okay? If I lost some people trying to do the stuff in blue, if you didn't understand what I just did over here, totally okay. Maybe ask me, in private if, you're a little nervous about speaking up. But either way, you get x is equal to 3/2, and that's going to be your final answer here. So, Deborah, I don't think I have time to do 86. It's just about 11:50 now. So if you want to see me about 86, we can, absolutely do that during office hours or, at some other time, okay? We might even have time in the next class, so we might come back to it. But in any event, that's it for today, guys. I'm going to end the recording here. Again, you guys should start getting your graded material back as early as today and as late as Wednesday, okay? So you'll get it back as of then at the latest. So everybody else, have a great day. Office hours today, 4:15 to 5:15. And please don't forget about your project packet, guys. Due date, fast approaching, right? Like 11 days from today, I believe. So in any event, have a good one, guys, and I will talk to you next time.